Welcome to the third lecture of week 6. Up until now, we have seen how we can do dynamic programming over graphs of bounded tree width. But in this lecture, we will see how to actually compute this. So this is about how to compute tree width of a graph G. Okay, so this is what this lecture. So given a graph G, let TWG denote the minimum tree width of G, or the minimum possible. Okay, so there are several questions that could arise here. Okay, so let me. Okay, so I have. So maybe okay. So what are the two questions we could ask? So we could ask the decision version of the graph problem could be, the decision version of the question could be, so input is G, K, my parameter is K, and the question is tree width of G at most K, right? Now, this problem was known to be FPT already from 1980s, but the first explicit algorithm was given by Baudelander by Hans Baudelander. It was given, first explicit algorithm was given by Hans Baudelander, who showed that design an algorithm for tree width running in time. If I k cube log k times n. So that also it also gave us the first linear time, because there is a linear dependence on the input size. Okay, but this algorithm is quite complicated, and we will not be doing in this course, but rather we will be giving an approximation for tree width as a parameter. Okay, so what algorithm we are going to present in this lecture today is the following. So the proposition we are going to show today, okay, or the theorem we are going to prove. So there is an algorithm that given G, okay, given G and rather given G and in rather let's say given G computes a tree decomposition, okay, tree decomposition of width at most 4 times tree width of G plus 1 in time n square, okay, where k equal to tree width of G and n equal to, right. So basically if you think of an approximation, then it's like if I were given an integer k, okay, so if you just think from the perspective of approximation, then what it means actually is that we can convert this algorithm into as follows. So what we can convert this algorithm into is as follows, right? So basically it tells that, look, I mean, if you could have run this algorithm, then okay. So I will give you an algorithm for this nature, okay. So and using this algorithm, actually we can actually come up with the following approximation to tree width. Okay, what is this? So approximation to the problem tree width. So this will output you either that, so you are given a g and k, either it will say the tree width of g is more than k, yeah, or rather strictly more than k, or output a decomposition of width 4k plus 1 in time okay. So this is what we will do, okay. Now, so that's our whole idea, but like remember in the last lecture we talked about this notion of separation number, right? So what is a separation number? So separation number of a graph was like, for a particular graph, was like min, size, balance, everything, but like we will try to do, okay. And then we said that, look, what is the minimum, if I say what is the meaning of the separation number of graph G is at most k, if I give you any induced subgraph, right, of G, then I can find a k size vertex whose deletion will have property that every connected component has size at most half of the original graph, okay. And we wanted to relate between zk and hk, but we say that, okay, it will not happen that way, but it will happen if we have some notion of weighted balance separator. So yeah, so today's lecture, let's try to do our first thing, okay. So this is a lemma that I would like to prove, and that will show something interesting, okay. Let G be a tree width, let G be a graph, let G be a graph such that tree width of G is at most k, okay, and W be an arbitrary weight function, arbitrary positive weight function meaning weight of every for every v, weight of v is greater than or equal to 0. So it's not negative, arbitrary positive weight function. Then there exists let's say W balanced separator of G of cardinality k plus 1. Okay. So what this tells us? It tells us that, look, you are giving me a graph G, okay. Okay. So you are giving me a graph G, okay, and there is a weight function W, okay. So okay, then I will find a W balanced separator of G of cardinality k plus 1, meaning I will find you a k plus 1 sized set, say S, so that if you look at the connected component, what is the property of connected component? For every connected component, weight of C is less than equal to weight of G divided by 2, where weight of G, or weight of, I should say weight of, and what is the weight of any set X? It's just the natural definition. Weight of X is like X in X, weight of X. Okay. So, if you have a set X, you just sum up the weights of each vertices. So, but basically this is why it is called weighted balance separator. That, and now notice that if you would have got this at most half of the original graph kind of definition, if we just would have put weights of every vertex to be 1. So, if the W is the weighted function which assigns every vertex 1, then we would have had satisfied this property. So, notice if a graph has tree width at most k, then in fact it has a weighted balance separator for any positive weight function. Okay. So, that is interesting. So, not only it has, so not only what does it show is that not only HK belongs to psi k, which was like, oh, graph with balance separator of size at most k for every connected component, but in fact it is like, I mean it is among the graph, like it is a graph with a amazing weight functions, like any weight function separator that it belongs to. Okay. So, how are we going to prove this? The proof is very, very simple, and it is, if you recall correctly, we proved a balance separator for trees, and it is going to be just exactly the same. So, now we have a graph G. So, we have a tree decomposition T and some xt T in Vt, and what is the size of any xt is at most k plus 1. Okay, because tree width of graph is at most k. Now, what we are going to do, okay, you fix tree decomposition. Okay, and you root the tree. Okay, you root the tree. Okay, and you ask yourself, so this is what we have to. Okay, so this is my root. Okay, and now I ask myself the following question: is XR the weighted balanced separator? Let us ask ourselves this question: is XR the weighted balanced separator? Well, what you know that if you delete XR, what is the property? That the property is that vertices appearing here, right? So, there will be a connected component, like the connected component of my graphs are either contained inside this vertices here or this vertices here, but they will not intersect. All their intersection vertices are contained inside XR. So, now I ask myself, okay, fine. Right? Look at these connected components, right? Is this property, does it property hold? I ask, for every connected component, is the weight of C at most weight of vertex set of G divided by 2? My answer is no, right? What is the meaning that my answer is no? My answer is no because it means there is a connected component here, which is either contained inside this green blurb or it is contained inside this purple blurb, okay, such that the weight of this component is more than the weight of this. So, what will I do? I said fine. Now, in that case, so if this was the weighted balance separator, we have found this, else you move your token to, suppose this is heavy, suppose this is heavy and heavy belongs to this side, then what will I do is that I will focus my, I will ask the part of the rooted graph, the part of the so if this is, that component is inside this, then now I move this token here, okay, that piece, and ask myself, well, I will ask the same set of question to, suppose this was like some other t, then now what will I ask? Second, is xt the desired weighted balance separator. Okay. Okay, so now let's okay. So now what happens is the following. Okay. Now now you delete xt. The moment you delete xt, what happens? Okay. So now I delete xt, okay, and then right, all the components of this pieces are going to be here, okay, going to be here, and including something that comes from the because of that red vertex, okay, so something, and all the components below xt from, let's say, here, okay, will be here into several components. Now, what could happen? If xt does the job, then we are happy. But notice what is happening at any point of time. At any point of time, the way our induction is that why did we move towards xt? Because it had a connected component whose weight was strictly larger than the weight v of t. It means if I look at the even sum of all the connected components here, right? What is the property? Because this had a connected component whose weight was larger. Any connected component that we are going to get here has a property that its weight is at most divided by 2. Right? So this is great, right? Now, so either this xt does our job, or look at one of its children, right? Like one of its children has a connected component, right? And that connected component is contained inside the subtree rooted, like if you look graph induced on the vertices in one of the subtree rooted at t, that connected component is heavy. Okay, so then what will you do? If suppose either this xt will do the job, or maybe suppose we had a different, then you will move the, say, t prime, say, hey, is this xt prime does my job or not? So notice that what is an invariant which I am maintaining is that the heavy component is in the subtree rooted at my current potential weighted vertex separator. Either that vertex does the job or I move below. But at each time, what is happening? At each time, what is happening? That we are moving away from the root r, right? So since my graph is finite, either we will terminate or we will reach a leaf. Then what is the property of that leaf? If you notice, if I reach some leaf here, then we know that if I delete this, suppose this xl, what is the property? That the weight of this xl is very heavy. Is like it is more than half of the whole vertex here. So the moment if I delete it, I know that every connected component has weight at most the weight of the original graph divided by 2, because xl itself has weight larger, and you are done. Okay. So this is very identical to the proof of balance separator that we did for trees, but now we are doing the weight function, and now rather than one vertex being the separator, it's a bag which is associated to the node of my rooted tree that acts as a balance separator. Okay. So now before we had one vertex because we were talking about tree, but now we are talking about graphs of bounded tree width or tree width k. So now the bag size xt is the size of the separator that we are talking about. Okay. So we have shown this. Okay. What does it implies? It implies that we have proved, in some sense, we have proved one, that actually we have proved that HK, if a graph has, okay. So now here is my HK, and suppose this is like weight function, but only 0, 1, and let us define arbitrary weight function, okay, arbitrary weight function. Like what I mean by arbitrary weight function means, like, given a graph G and any weight function W, you have a weighted balance separator with respect to that, okay. And with 0, 1, it's only those weight function. So I'm taking graph G, but I've restricted myself to only 0, 1 weight function. So what we have shown now, that HK actually be like, if you have a graph of tree width at most k, then actually it has a weighted balance separator with respect to zeta z, okay. So this is what we have shown, that HK belongs to this family of graph. But now what we are going to show to you, okay, so partial converse, and that is what will constitute our algorithm. So my lemma is, if G belongs to, okay, if G belongs to say, I will write it explicitly. What is the meaning of this? Okay, meaning for every weight function W from V0 to some 0, 1, okay, okay, there exists a weighted balanced separator, there exists a weighted balanced separator of size k plus 1, meaning for every weight function W from Vg to 0, 1. What is the meaning of this? So I will be able to find some set X, set S of size k plus 1, okay, 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 rather let us say, okay, size k plus 1, such that for all component C, weight of C is at most weight of vertex set of G divided by 2. Okay, that is it. If G has this, then I am going to show to you first that the tree width of G is at most 3k plus 3. Okay? Okay. So let us try to understand what does it say. It says that, look, I have a graph G such that, what is the property of this graph? That if you give me any 0, 1 weight function, okay, then I will be able to find a balance separator of size k plus 1, like weighted balance separator of size k plus 1. Then what can you say? Then I say, hey, if that is the case, then I will be able to show to you that the tree width of this graph is at most 3k plus 3. Okay? Okay. So what will we prove actually to you? Okay. So I am going to prove this to you. And in fact, I am going to prove slightly more general theorem. In fact, what I am going to prove, कि for every W subset of Vg, okay, with is at most 3, the graph G has tree decomposition okay. the graph G has a tree decomposition T, xt, okay, of width at most 3k plus 3 such that W is subset of XR W is subset of XR for the root R of T. Okay? So, we will always assume that T is rooted at some R. Okay? So, what this tells us that look, not only this, you give me any set W of size at most 2k plus 3. In fact, I can come up with a tree decomposition where the root bag will have the property that W is contained inside that root bag. Okay? So, I mean, so this is, and you will see that why we will need this, because we are going to prove our statement using induction. Okay? We are going to prove our statement using induction. Okay? Okay. So, proof is by induction on number of vertices of my graph. Okay? So, what is my base case? I am going to ask if number of vertices is less than 3k plus 4, okay, then if n is at most 3k plus, then we will return one node tree decomposition of G, right, and right, that is it, one node tree decomposition. So, basically what will you do? You just assign a node, it is a root everything, and what is XR? XR is basically V of G, that is it. And you notice that it satisfies all the property. So, from now onwards we are going to assume that the vertex set of this graph is strictly greater than 3k plus 4. Okay. Now, let W subset of Vg, okay, be such that you gave us, okay, and what is the size of W is 2k plus 3. So, what I am going to do, that given this W, I am going to construct W tilde, okay, I am going to construct W tilde which will contain W, okay, by what? So, suppose this is my W, okay, this is my W, but the size of W is strictly less. So, what will I do to make W tilde? Okay, I will add arbitrary vertices in V, arbitrary vertices from Vg, so that size becomes exactly equal to 2k plus 3. And notice, because we have that many vertices, so we can always if you gave me W whose size is much smaller than or strictly smaller than 2k plus 3, then I will arbitrarily add some set of vertices from my graph and make a set W tilde. And notice that if I can come up with a tree decomposition with W tilde being the root, then definitely that has a property that even W is contained inside this, because W tilde contains W. So, just for simplicity, okay, we will rename W, okay, W tilde is nothing but W, and W tilde has size exact and we just renamed it, okay, otherwise it has size exactly equal to 2k plus 3. Okay, okay, okay. Now, what will happen? Okay, so now what I am going to do, I know that my graph G has weighted balanced separator for every 0, 1 weight function. Okay. So I fix a weight function. What is my weight function? So my f of vz to 0, 1 is, so basically what I would like to do is that I would like w to be separated very nicely. So then what I'm going to do is that I'm going to assign f of v is 0 if v does not belong to w, and f of v is 1 if v belongs to w. So notice, what is the weight of vertex set of G? Is nothing but equal to w. Okay. So it means there exists a separator. Okay. There exists a separator S. What is the property of this set S? Now look at this property of set S and look at every component. Okay. So what is my component? Suppose we have component C1 to Cm. Okay. M components. Okay. The property is that if I look at weight of Ci, okay, it is at most weight of vertex set of G divided by 2, which is nothing but at most weight of, it is nothing but cardinality of W divided by 2. And what is weight of Ci? Is basically, this is nothing but W intersection Ci. Right? So, okay, this is what it is. Okay. 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 Now, to apply induction, what we like to do is that to apply induction, I would like to say, okay, fine. I will try to say that, okay, find I will make a graph Gi. What is a graph Gi? It is graph G intersect is Ci union S. So basically, so what we have done here now is that we are taking this as one piece of the graph. Okay. So I'm going to decompose this. Then I'm going to decompose this in as a one piece. I'm going to decompose this as one piece, and so on and so forth, right? So this is what Gi means. But now I would like to apply induction. Okay, I will like to apply induction. Okay, so to apply induction, first of all, I need to show that Ci union S is strictly less than Vg, right? That's one thing. And I have to define what my Wi is. Okay. So the tuple on which I'm going to apply induction, because what I'm proving inductively I'm trying to prove that given a graph G and a set W of particular size, okay, I can come up with a tree decomposition such that the root back contains the Wi specified. So now I'm going to call induction on this particular graph. So I need to show that this is this, and I'm going to set Wi as what I'm going to set Wi is nothing but W intersection Ci union S. This is what I'm going to set. So the intersection of W which I started with, this blood, and set S. So I also need to show, to apply induction, that the Wi is at most 2k plus 3. 2k plus 3. To apply induction, I need to show what was that I started with? Yeah. So we started with 2k plus 3. Yeah. So I need to show that this is at most 2k plus 3. Okay. Okay. So let's try to do each of these things. Okay. 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 Now let's try to show bound, let's see what is Vi, or rather, let's okay, I would like to upper bound Wi intersection Ci. Okay. So, what is this? Wi intersection Ci is okay. Let's okay. Let's call Vi as Ci union S. And now what I am interested in is that what is Vi intersection capital W. So, what is the Vi intersection capital W? So, if you notice what is Vi intersection capital W is upper bounded by what, like, where could W lie? W is going to be either here or it is going to be contained inside S in this portion of the graph. So, which implies that Vi intersection W is nothing but upper bounded by Wi, which is upper bounded by W intersection Ci plus cardinality of S. But what is the W intersection Ci? W intersection Ci is upper bounded by cardinality of W by 2 plus cardinality of S. What was cardinality of W? Cardinality of W was exactly equal to, if I recall correctly, we made it exactly equal to 2k plus 3. Okay. So, 2k plus 3 divided by 2, and what was cardinality of S was exactly equal to 1. So, this is equal to k plus 3 by 2 plus k plus 1, which is 2k plus 3 by 2 plus 1 is 2.5, right. So, what does this imply? This is exactly equal to, strictly less than equal to 2k plus 3, okay, which was equal to W. So, what does this imply? It implies that there exists a vertex of W, okay. What does this statement implies, right? It implies that there exists a vertex of original W that do not belong to, there exists a vertex of that do not belong to Vi. What does that imply? It implies that cardinality of Vi is strictly less than cardinality of original graph. So, it is good for applying induction. Okay. So, we have shown that this is strictly.